is an example of a stratigraphic fault, also known as an up-dip pinch-out trap. This is where sandstone slowly turns into shale. Remember that shale and sandstone are both sedimentary rock, but because shale was made from clay and mud, it is not porous, where the sandstone made from sand is. Anyway, in this trap, the deposits of sandstone are next to the deposits of shale before they were all lithified. This could have occurred at the bottom of a fast river bed where the sand was deposited first, but where the clay was pushed just a little bit further out. Then later, under some geological event like an earthquake, the sedimentary rock was tilted. The result is that this bed goes from high porosity in the sandstone to low porosity in the shale. When oil later migrates into this area, it gets trapped by the shale and the oil accumulates in the sandstone. Stratigraphic means depositional. It was the way the particles were deposited. Reefal traps are formed where millions of shelled animals died, like clams, snails, coral, and where they got buried on the bottom of the ocean. These shells, made of calcium, are buried and crushed into calcium carbonate, or limestone rocks, our standard reservoir rock here in the UAE. Reefal traps are excellent places to find oil. Oil migrates into them from the source rock and flows to the top of the trap, where it will be stopped by a cap rock. They look like an anticline, but they are not. Reefal traps are stratigraphic, meaning they were formed during the deposition of layers of dead animals. In this picture, we have combination traps, commonly known as angular unconformity traps, are composed of rock formations created from both deformation and deposition. First, there is deposition, then lithification into rock. Next, it is uplifted above the sea level. Then it's tilted from earthquakes or plate movements. Then there is horizontal erosion at the surface. Then it sinks below sea level, and there is a new shale deposition. Next, this new shale is lithified into a cap rock. And finally, oil migrates into the reservoir rock and is trapped by the shale. Lots of steps have to occur before we have a combo trap. Geologists and petroleum engineers look for these traps because they can hold large amounts of oil and gas. The final section in this chapter is about reservoir pressure. Reservoir pressure is that pressure that exists inside the reservoir, and it's what drives the oil out. And the drilling engineers, petroleum engineers, and exploration engineers need to understand the kinds and types of pressures that exist so that they can safely extract the oil and bring it to the surface. The definition of pressure is force divided by area. In the oil business, pressure is measured in PSI, pounds per square inch. When you go to wash your hands and turn on the faucet, the pressure on the water at the faucet is about 60 psi. A typical fire truck, when pumping water to put out a fire, will generate about 400 psi. Underwater divers measure the amount of air in their tanks with the psi, and a car mechanic measures your tire pressure with psi. Let's take a look at pressure. You have a bowl of water with a fish, and you place 3 balls of various sizes into the water. Note how the depth of the water increases. Because you put 3 balls in, one will not fit in the water but will stick out. The ball that sticks out is still stacked on the other 2, so it is said to exert overburden pressure. It causes pressure on the other balls. The space between the 2 balls underwater is called pore pressure. Your fish is now in deeper water. In this space called pore pressure, the fish will feel the pressure. So the pressure on the balls is called overburden pressure and increases when you stack more balls. The pressure in the pore space is called pore pressure and increases when the water column rises. Pore pressure will increase up until the bowl is filled up at the top and then begins to overflow. Let's look at this in another way. Here we have a fish, again under normal pressure. If you add layers of rock, will the pressure on the fish increase or decrease? Pressure on the fish will only increases or depth increases. Let's look at the formation of these rocks closely. In this picture, there are 3 rows of rocks. In the first row, the rocks are in a single layer and are uniform in size. In the second row, you see a deposition of 2 layers, but still uniform in size. In the third row, the deposition has increased to 3 layers, but the size of the rocks are not uniform in size. They vary in size from large, medium to small. Like with our bowl of fish, as deposition continues, overburden increases on the rocks only and will eventually compress and crush the grains, squeezing out most of the water. In normal pressure development, the top row has high porosity with low pore pressure. As you descend to the lowest row, the overburden pressure of the rocks and the deeper level of the water causes both the porosity to decrease and the pore pressure to increase. Our hypothetical fish is experiencing more water pressure because there is a higher water column above it, and it is becoming more difficult for the fish to swim between the rocks because the porosity is decreasing. But the increased rock pressure is not affecting the fish. In drilling for oil, we use the following mathematical formula for approximating bottom hole pressure. Normal pressure equals the water gradient times depth. The water gradient for normal pressure in salt water equals about 0.5 psi per foot. It will change slightly with salinity, but 0.5 psi per foot is a good approximation. For all of you who use the metric system, 3.28 feet equals 1 meter. So using our formula, we can answer the question, what is the pressure at the bottom of a 10,000-foot well going to be? Well, it is P equals 0.5 psi per foot times 10,000 feet, which gives us 5,000 psi. Here is another example. In a U-shaped tube, I put a valve here midway down in the left-hand tube. Then I fill the right-hand tube with water to the top. As you can see, the water flows into the tube until it is stopped by the valve. When I open this valve, the level of water equalizes in the tube so that the water fills both sides of the tube equally. As long as it is water, the two levels will be equal. This is called a balanced system because the water can flow up and down and both sides will be equal in height. The same thing is true in the rocks at the bottom of the ocean. As long as the water is connected to the surface, it can move up and down at an equal rate. Now let's do the same experiment again. I close the valve, put in some oil, and then top the right-hand tube with water. Now, when I open the valve, because the density of oil is lighter, the fluid levels in the U-shaped tube will not be equal. This time, the level of the fluid in the left-hand tube with oil will be higher. This is still considered normal pressure because the pressure on the right side is caused by the water column.